Start recording. Yeah, start recording now.
Mm-hmm.
This section that have the lessons.
Mm-hmm.
You see videos.
Mm-hmm.
So if you click on it, you're going to see a set of videos.
Okay,
The
hold on, let me
default,
call my one.
the default look is is like that.
Alright, we'll look on my one, look at the light.
Yeah.
Oh yeah, I see them.
Right. So the default look, they kind of like in a two column thing. At the
Mm-hmm.
at the top left, when you mouse over it, just above where it says all, to the left of it, when you mouse over it, it says list view. You seeing it?
Well, it's three, seven, seven on my own. Three column.
Oh, you're seeing three column? Okay, fine.
Mm-hmm.
Move your, go up to the top and to the left. When you mouse over, you should see something that says list view.
So what?
It says list view
List view.
when you mouse over it.
When you mouse over the are all items.
All right,
Oh
come
yeah,
back
yeah,
to
yeah,
my.
yeah.
You
It's
seeing
alright,
it?
it's alright. I see it. Yeah, I see
Yeah,
it.
click on it now.
Okay, yeah.
Yeah,
It's a
see,
watch trying to get the time beside it.
right. So it's easier to read that way.
Okay.
Yeah, so I work with it in list view because I can read more things. I can see that it has to do with debug and show commands. I can see the time and
Mm-hmm.
the watch section. If you were watching it and you stop before it finished, it will tell you what percentage of it you have watched.
Alright, this I realize okay, debug fish basics. Okay. It just covers some things.
Yeah, yeah.
Okay.
The videos don't cover the entire
Right.
content, but it cover
Okay.
parts of each parts of the different chapters.
Okay. Okay.
Yeah. So that's what I wanted to show you because I know sometimes the videos help.
Yeah, yeah, definitely.
Yeah. All right. So how things in terms of what you were able to cover?
All right. I cover all of your slides, but not in terms of it's like reading but not retaining, tired feels like.
Hmm.
But I think I'm on the ball now, so the rest of this week I think I'm gonna cover you say all 8 chapters plus more now.
Right. So you're going to get
Yeah.
8 more chapters today.
Okay, okay. Yeah, one up for it one.
All right. So
Mm-hmm.
um, so on the main page,
Mm-hmm.
we're going module two.
Mm-hmm.
When you click on module two, you get to that second set.
Okay. A spanning tree.
Right, so we're just going to start with the first one, which is spanning tree.
Mm-hmm.
Okay. So the objectives we're going to cover under spanning tree is STP, which is
Mm-hmm.
spanning tree protocol. Then we look at the rapid spanning tree protocol. Then we're going to details of a spanning tree, but not rapid spanning tree, just strictly spanning tree.
Hey, please, I get overcast.
Sorry?
Hey, please get dark family call.
Oh,
Hey, overcast.
Yeah. And then we go to a rapid spanning tree.
Okay.
So the first thing is we want to look at what is the problem that spanning tree is designed to solve. So if we don't have spanning tree, what is the problem we might experience on the network?
Mm-hmm.
And that is broadcast storm. So we're showing an example of broadcast storm happening here. So this computer here being used by
Mm-hmm.
Bob wants to send a single frame, right, some kind of message to, let's say, to Archie. So when Bob sends that frame, it gets to the switch. But currently, the switches don't have the MAC address of Archie's computer, so they don't know exactly where Archie is located because the MAC address tables are empty. So switch 3 here is going to send out a flood. So it's going to send the information that is sent by Bob. It's going to be flooded to both switches, to switch 1 and to switch 2. Now, so as not to crowd the slide, we are only showing the part that goes to switch 2. Right? So when it goes to switch 2 also does not know where Archie is. So switch 2 will flood and will flood and it will go out every port except the port on which the frame was initially received. So it's going to send that out to switch 1. Of course, it's going to send it out to Archie as well. But send it out to switch 1. Our switch 1 also does not know where Archie is, so switch 1 is going to flood. So it's going to send it out to Larry and it's going to send it back to switch 3. So switch 3 is going to receive the same information that it had flooded. Now, in that case, switch 3 is going to see it like it's a new traffic. And assuming that Archie has not yet responded, so switch 3 still don't know where Archie is. Switch 3 is then going to flood that again and it's going to get back to switch 2. And as you see here now, it's just going to be continuing around the network. Now, this can be a bad thing with one computer, but can you imagine early in the morning when several persons are booting up their computers and all those persons now are sending out, let's say, a DHCP broadcast. So what you have is, let's say, 50 persons at about 8 o'clock thereabout turn on their computer, and those 50 persons sending out DHCP broadcasts. So that now is going to cripple the network. That is one of the issues with spanning tree. When you don't have spanning tree, right? That storm of multiple broadcasts happening across the network. Right? So the question then is, how would spanning tree solve this problem? And well, uh, before we go on, this slide here is this. I've actually talked about this from the previous slide, but just to mention again, the broadcast arm, the forwarding of frame repeatedly on the same links, and that is just consuming the capacity of the link or the bandwidth of the link. It also causes MAC table instability. Now, what we mean by that is that initial traffic would have been sent out by Bob. So as far as switch 3 is concerned, initially it's going to see Bob's MAC address as being right at this port here. When the flood happens, that traffic goes out, so switch 2 is going to now say Bob is assigned to gig 0/1. When switch 2 flooded, switch 1 is going to see Bob as being a part of the gig 0/1. Switch 1 floods that traffic back down to switch 3. Now, switch 3 will see Bob as being a part of gig 0/1 and not 0/13. So that is what we call the MAC table instability, because the switch would have recorded Bob as being located at fast Ethernet 0/1, but after the flood, it's going to now see Bob as being a part of gig 0/1. That makes sense?
Well, kinda coming out, get part of it.
All
No
right.
get full part of it.
Okay, let me go again.
Mm-hmm.
So here is Bob right here, right?
Mm-hmm.
Bob is sending a message to say Archie. So when that message comes to the switch is going to record Bob's MAC address right here.
Yeah.
Right? So the flood goes to switch 2 floods that out to switch 1, and switch 1 floods it down to back to switch 3.
Mm-hmm.
Now each of those flood is having the source MAC address as Bob's MAC address.
Oh.
So
Oh.
as far as switch 3 now is seeing, it is going to assign Bob to gig 0/1.
Okay.
So because a switch generally will try not to have a MAC address, the same MAC address assigned to multiple ports, it's going to remove the MAC address after some time from fast Ethernet 0/13 and assign it to gig 0/1. With me?
Yeah, but the new assignment, explain that new assignment for me.
Well, the assignment, how a switch assigns a MAC address to a port is simply
Mm.
because it sees traffic coming from that MAC address.
Yeah, yeah, but it's with the one for Archie, it changes, is it?
No, not Archie.
Oh,
So we're not looking at Archie responding as yet. We're just looking at the same traffic that is coming from Bob. What is happening to that
okay.
traffic? Right, so the traffic comes from Bob, gets to switch 3. It
Mm-hmm.
is flooded to switch 2. It is also flooded to switch 1. But just for the sake of the discussion, we're showing only one part of it. So you know that the
Okay.
diagram being crowded.
Mm-hmm.
So we're looking at it being flooded to switch 2. So once that traffic gets to switch 2 will then say it's going to assign Bob's MAC address to gig 0/1 right here, where my red dot
Okay.
is.
Yes. Mm-hmm.
Right? Switch 2 is then going to flood the traffic. That traffic comes over to switch 1. Switch 1 now sees the traffic coming from Bob's MAC address and assign Bob's MAC address to gig 0/1.
Oh, coming from Bob McAdress. Okay.
Right? Because this all this traffic we're looking at is what initially came from Bob.
Yeah, yeah.
Switch 1 is going to flood that traffic, so it goes back down to switch 3.
Mm-hmm.
Now when it gets to switch 3 sees the same traffic coming from Bob. And switch 3 says, okay, Bob is now at gig 0/1.
Okay, that part we know again.
Right.
Yeah.
So now it's going to remove Bob from fast Ethernet 0/3. It erases Bob MAC address from that port and put Bob's MAC address on the gig 0/1. You see?
Yes.
Right. So that is the MAC table instability. And that can cause problems now because if somebody is trying to send something to Mac to Bob, the switch might send it to gig 0/1 when Bob is not really there. So that's the issue with the MAC table instability. The other one that could happen is multiple frame transmission. Now, if I look back here, multiple frame transmission. So let's start again. Bob sends a message. This is supposed to get to Archie. This message is going to be flooded to switch 2. It's also going to be flooded to switch 1. Right? So let's take the switch 2 part first. So it gets to switch 2, and switch 2 floods this message out all ports except the one it receives on. So it's going to go to switch 1 and it's going to go out to Bob. So Bob has now received one copy of the message. With me so far?
Yes.
Okay. So the next part now, let's look at what happened when it was flooded. So simultaneously when it is being flooded to switch 2, it was also being flooded to switch 1. So when it gets to switch 1 then floods that out to switch 2. So now switch 2 receives the same traffic, but because it's coming on a different port, switch 2 believes it's a different frame or a different message, and then also floods that to Archie.
Yeah, I get it now. Yeah.
So Archie now getting two copies of the same message. So that can cause problems. It could actually cause the Ethernet software on Archie to be corrupted, or it can cause Archie to try and respond to the same message twice, which then put more unnecessary traffic on the network. So those are the issues we have when spanning tree is not in place. So to fix that, we need to have spanning tree. Now this is how spanning tree is going to work, right? So spanning tree will look at the multiple ways of getting, and this is before any traffic is sent at all. So once the switches are turned on, right, spanning tree will try and find out how many ways does switch 3 have to get to switch 2. So based on this, it can get to switch 2 by sending traffic directly to switch 2, or it can send traffic to switch 1 and then switch 1 forwards that to switch 2. So two ways of getting to switch 2. Also, there are two ways of getting to switch 1. It could send the traffic directly to switch 1, or it could send traffic to switch 2 and then it's sent over to switch 1. Now, each of the three switches are going to be doing that, not just switch 3, but each of the three switches. Now, those switches will then make a decision to ensure that they only have one way to get to each destination. So in this case, looking from the point of view of switch 1 is ensuring that it has only one way of getting to switch 3. So it could send traffic directly to switch 3, or it could send it to switch 2, and then from switch 2 to switch 3. It needs to make a decision as to which one of these paths is the best path. So in this case, we are saying it has made the assumption that the best path is from switch 1 directly to switch 3. Therefore, what it does is the path between switch 3 and switch 2, it blocks that path. And that is why we have this X there. So as you see here, it says block. So because this path is blocked, then we now only have one way to get from switch 1 to switch 3. Now this blocking is a software blocking, so in terms of the hardware, the cables and everything, all of that is still intact. But the software, spanning tree software, just block one of the ports. That makes sense?
Yes, it does.
Right, good, good. All right, so that is just more from a theoretical look as to how spanning tree works. Give me one sec there. All right, back with you. So I want to now go into a little more detail with that. So spanning tree will have some categorization for the ports, right? So some ports are going to be in a forwarding state and some are going to be in a blocking state. Now, forwarding state means that it will allow traffic to go out or be received on those ports. And blocking means no traffic will go out and no traffic will come in. Right? So those are two of the states that the spanning tree will have. Now it will also categorize the ports as you're going to have root ports and you're going to have designated ports. You're going to have root switch and non-root switch. And we'll talk about which one is going to be the root and so on in a little while. But for the root switch, all of the ports on the root switch are going to be in the forwarding state, meaning all of them will be allowing traffic to be sent out and traffic to be received. Any switch that is not the root, right, it is not the root switch, but it has a port that is leading towards the root switch. That port that is leading towards the root switch will have its port as forwarding. And then now, on each land, you're going to have ports on land that is called designated ports. Now, let's just go back a little. So, like let's say between switch 1 and switch 2, right? So, whichever port that is set up to forward traffic, you're not knocking.
Not anymore.
Okay. Well, you had heard it before.
Yeah, yeah.
I don't know where it's coming from. All right. So, whichever port that is going to be forwarding traffic on the segment and it's not a root port, it's going to be called a designated port. So, one of the ports is going to be a root port, and the one that is not the root port is going to be a designated port. We'll see in more detail in a little while. All right. So, we have um, yeah, so that's it for that part. Um,
Hold on, just a question. In terms of the interface, possibly how much port can I hold for an interface?
well, with a switch, generally an interface is a port. So
Mm-hmm.
it is one. One physical port is an
Mm-hmm.
interface.
Mm-hmm. You said forwarding and blocking port. That's what I'm asking.
Oh, yeah. So let's look at this. We'll have to go back up, but just to answer that question.
Mm-hmm.
So like I want to find a good enough diagram to show. Yeah, let's use this one. But we're going to have to go back up, so all of those that we skip. So notice we have this is a root switch, and we have these ports listed as DP. So these are the designated ports. The ports on the root switch are going to be designated ports, meaning they are ports that can be used to forward traffic, but they are not route ports. So as long as the port is being used to forward or receive traffic, it's called a designated port. Over this side on switch 2, any port that leads directly to the root switch is called a root port. So this port here is leading directly to the root switch, so it's a designated port. Right? So this port, sorry, I'm not designated, root port. So this switch port is a root port because it's leading directly to the root switch. That makes sense so far?
Yes.
Okay. Then now, notice we have some other ports like this one going out to the PC. That's going to be a designated port because it is being used to forward and receive traffic, but it is not the root port. So as long as it is being used to forward and receive traffic, and it is not the root port, then it is going to be the designated port. So we're going to have multiple designated ports, but on
Uh,
each switch we'll only have one root port. Yeah, go
so
ahead.
can I conclude that if a switch of 24 interface is also 24 ports,
Correct.
but some ports will use as root and some will use as block or different functions.
Right. So the
Okay.
root port is the port that is leading towards the root switch.
Okay.
And then all other ports that are being used to receive and send traffic are called designated ports. Good?
Yes.
Okay. Now, all other ports, any port that is not a root port and is not a designated port, it is going to be a blocking port. So if it's not a root and it's not designated, then it's blocking. All right?
Yes.
Okay, so let's go back up now to the slides we had skipped. So this is where we had stopped first, right? Where we had talked about the root switch. So the root switch will have all its ports in forwarding mode, and they are going to be called designated ports. The non-root switches, they will have ports that are in forwarding, right? So the ones that are going to the root switch will be in forwarding, and then you have other ports now that are going to be sending and receiving traffic that are going to be in forwarding as well. And those are going to be called designated. And then any other port, as long as it is not the root port and it is not the designated port, then it is a blocking port.
Oh, I'm gonna ask again to you, lad.
Mhm.
Um, when I was at digital, you have people who used to have the camera system where they could have viewed the system from remote location.
Mhm.
With Flow, it was a big problem. They used to like send them a static IP and they used to, but I realized people switch service and then they have to call in the ITV so they can't view their camera because it seemed like some port block from them seeing what's going on at the DVR from a remote location. You ever heard of a case like that?
Yeah, but that's a different thing though. That's different from what we are talking about here.
Okay, total. Okay, okay.
Yeah. So in that case, the ports that might have been blocked are the TCP or UDP ports.
Okay, okay, the software type thing.
Right. While these ports we're talking about now are the physical ports.
Okay. All right, just relate the two now then. All right.
Right, right.
Okay, good.
Okay. So every switch is going to have an ID. The ID is called the root bridge ID. So um, let us use the term root bridge ID because initially they start out with bridges. Right? So rather than change that says root switch ID, they just keep the term root bridge ID. So every switch is going to have a bridge ID. The root bridge ID is the ID for the root switch. So whichever switch is the root switch, it will have the root bridge ID. Um, that switch is going to be sending out hello, which is basically a message that says this is my ID. So and it does that every 2 seconds. It sends out a message that this is my ID, this is my ID. So the sender's bridge ID is in that message that is being sent out. The message is called the BPDU, which is Bridge Protocol Data Unit. In that message, it has it's going to have the root bridge ID, and the sender is going to have its own ID as well. It's also going to include a cost. Right? The cost is based on the bandwidth of the ports. So each port will have a cost, and that changes depending on the bandwidth of the port. The In the hello from the BPDU, it will include the cost to get to the root. In other words, based on the bandwidth the bandwidth of the port leading to the root, it has a cost, so it's going to include that cost in its messages. Right? And then, of course, it's going to have some timer values. So one of the timer values is the hello timer to say how often am I going to be sending these messages. It has a next timer called a max age timer, and it has a next timer called a forward delay timer. So all of those timers are going to be included in the in the hello message. Alright, so the first thing that must happen when we power up these switches is for the switches to go through an election process. That election process is what the switches are going to use to determine which one of the switches is going to be the root switch. So they're going to do their own election.
I heard what you're saying about. I just know it's a register, you know. When you
Yeah,
say election process,
right,
that the person who configures will do that, but you said no, it's going to be a process. Okay.
right. Now the person who configured could actually do it, but the default behavior is that the switches will go through their own election process.
Okay. Okay.
Alright, so the first thing that's going to happen with the switches, right, is every switch will put itself as the root. So everybody is going to say, I am the root. And they are going to send out their message saying, I am the root. Right? Now, in that message, it's going to have these two things, my bridge ID and the root bridge ID. Right? So it's going to have itself as the whatever ID it has for itself, it's going to put that same ID as the root, because it's saying I am the root. But as it receives from other switches, it's going to compare its own ID with the root ID coming from other switches. And whichever ID is lowest is the one that it will now elevate to the status of being root. So for example, switch 2 would have initially sent out a message to say my bridge ID is 32,769 0200 and it is going to also say the root bridge ID is the same number, right? But when it receives from switch 1 and it sees that switch 1 has a low number because switch 1 is 00200 0001 so it sees that switch 1 of a low number, so it says okay, well switch 1 is the root then. With me?
Yeah, pass the time.
Yeah, right. So once they're listening to each other, and any switch that now has a lower number, it says, okay, I'm going to accept that you are the root. So based on what we have here, switch 1 has a lower number, right? So switch 1 is going to be the root of this network. So everybody, all the switches accept switch 1 as the root. Yeah? So that's how they go about selecting the root. Now there are two sets of numbers here. One of them, the first one, the 32,769, is called the priority, and then the second part is the switch MAC address. Right? So the ID is a combination of the priority and the MAC address. So that's how it gets the ID. But note though that the MAC address, sorry, not the MAC address, the priority is going to be the same for all switches by default. Or the priority is 32,768. That's what the priority is. 32,768. Now you notice that on the slide we have 32,769. That is because the VLAN ID is then added to the priority. So we're looking on in this network and just making the assumption that all the switches are operating on VLAN 1. And so when they add the 1 for VLAN 1 to the priority, then they all get 32,769. With me?
Yes.
Okay. So based on that, the priority, which is the first thing they would have used to determine the root switch. But because the priority is now equal, then the MAC address becomes the tiebreaker. Because every switch must have a different MAC address. Alright, so I would have gone through this already. As we say, S1 wins the election. So S1 is now the root. Now once the switches know which one is the root, the next thing they need to start to establish now is things like the root port, designated port, blocking port. Right? They also need to start to determine the cost of each port. Now we'll see the actual costs for the ports later, but we're going to make some assumption here and use that to simplify the discussion. So let's say the cost of the port between gig 0/1 and 0/2 is 4. And these costs don't have units, it's just 4. So the cost here is 4. and then the cost between switch 1 and switch 3 is 1. So in that case now, and the cost right here is 5. Sorry, not 5, 4. So we have 4, 4, 1. Okay? So switch 2 is going to advertise to switch 3 to say, if I need, and this is switch 2 talking, if I need to get to the root, it would cost me 4. So it sends that to switch 3, right? If I need to get to the root, it would cost me 4. Switch 1 is going to say, if I need to get to the root, it would cost me 1, right? But of course, if switch 2 is going to travel this way to get to switch 1, it's going to be 4 plus the 1, make it 5. Right? So the cost to go this way is going to be 5, while the cost to go that way is 4. Make sense so far?
Yeah, well, you said through the cost unit, that's when I fully understand the assigned cost. So.
Yeah, so don't worry about how we get the cost just yet, because right now we're just picking some number randomly, right?
Okay,
We
okay,
will show a slide with the actual cost values later.
okay.
Right, so we're just picking some number just to simplify the discussion. Right, so those costs now are going to be used to determine which port is going to be the root port, which port is going to be the designated port, and which port is going to be the blocking port. Those costs is what we are going to use to make that determination. Right. So here, so note we have the cost now. So you see 4 to get to, from switch 2, 4 to get to the root. From between switch 2 and switch 3 is another 4, and switch 1 and 3 is 5. So we have those cost values. So as I said, these costs, we're just randomly putting some costs here. These are not based on any standard right now. We're just picking some numbers. So using those numbers that we had just picked, looking now from the root, remember switch 1 is the root. So switch 1 is going to be sending some traffic out. Right? When switch 1 sends information out, that is going to come out with a cost of 0, because switch 1 is the root. So to get to itself, it shouldn't cost anything. So any messages sent out by switch 1 will have a cost of 0. So it sends out a cost of 0. Now the cost here is 4. So switch 2 says, if I need to get to switch 1, it's going to cost me 4. Right? Alright, so this direction now, switch 2 is saying, okay, it's telling switch 3, it costs me 4 to get to the root. Right? The cost at this position right here is 4, because this length is 4. So switch 3 now is going to say, well, in that case, it's going to cost me 8 to get to the root if I go this direction, because it's going to cost me the 4 for this link, and it's going to cost me the 4 on this link. Make sense?
Yes.
Right. So if switch 3 is sending information this way, it's going to have a cost of 8. However, if it sends information that way, it's going to have a cost of 5 because this link is 5. So in terms of the total cost now, we have 4 this direction, we have 8 this direction, and we have 5 this direction. So the switches now are going to look at those costs and make decision based on the lowest cost. So I'll come back to this one. So these are the actual costs now. So if the port or the interface on the switch is 10 megabits per second, the old costing method would be 100. So there are two. The newer method, which is based on the standard that came out in 2004, the cost would be 2 million. If we use the old method, it would be 100. If the port is 100 megabits per second, based on the old costing, it would be 19. Based on the new costing, it would be 200,000. If it's a 1 gigabits per second port, then the old cost would be 4. The new cost is 20,000. If it's a 10 gigabits per second port, the old cost would be 2. The new cost is 2,000. If it's 100 gigabits per second, the old cost, they didn't actually have a cost to it. But what would happen? It would just use the lowest cost because there is nothing else for it to go to. So even though they have NA here, if we are using this whole costing method on one of these links, it will actually choose the two.
I observed that the higher the port speed, the lower the cost.
Exactly. Because the decision is going to be I want to use the port that has the best bandwidth.
Okay.
Right? And therefore we use the one with the lowest cost.
Yeah.
Make
So that
sense?
the port that yeah, terabyte port exists?
Yes, man.
Yeah, okay.
Yeah, but those are going to be more than likely fiber.
Okay.
But yes, they do. All right. So those are the costs. So I'd skip these because this is what we had gone through before. It's just that it's just naming the ports now. Switch 1, big 0 slash 1. So if we look back, switch 1, big 0 slash 1. Right? And it's saying so that port is forwarding. Right? The interface is on the root switch. Right? Going back up. This is the root switch. So gig 0 slash 1 on switch 1 is on the root switch. And then so it becomes a designated port on that link. Going back up, because this is forwarding, then it must be designated because on the root switch, the port has to be designated. It could not be root because a root port is how to get to the root. So since this is already the root, it could not have a port to say how to get to the root. So all ports on the root switch are going to be designated. And as you see, all of the other ports are designated. The only one that's blocking is switch 3, big 0 slash 2. So switch 3, big 0 slash 2. Now, why would this port be blocking? Let's take a look. So remember, spanning tree needs to have a single path to get to a single path through the network. Right? So right now, looking from switch 3, if switch 3 need to get to switch 1, if it travels this way straight up, then the cost is 5. If it travels this direction, the cost is going to be 8. So which direction is the best one for it to travel?
You asked about switch tree, right?
Yes,
The cheapest one, you say?
right. Which is?
The switch tree is the one directly.
Right. Good. So it would have then said, okay, since that is the best way, I'm going to make this port
Mm.
my root port, and my root port must be in a forwarding state, meaning I can send traffic out and I can receive traffic on that port. Right?
Mm-hmm.
Now remember, it only needs one path. So this other path has to be blocked
Yeah.
because it cannot have multiple paths to get to the destination or to get to the route. So since it already select this path as the cheapest path, then it's going to block this
Yeah.
one. Same thing from switch 2. So switch 2 says if I go this direction, then that's going to be 4. If I go this direction, it's going to be 4 plus the 5, so it will have been 9. If switch 2 was to go this direction, it's going to be 9. So switch 2 is going to make this port, the one directly to switch 1, the forwarding state, and also it's going to be the root port. And then it's going to block this. Right?
Yes, yes.
Right. Now, I just said this is going to be blocked, this port and this port blocked. But that don't happen on a network, right? It usually just block one of them. Right? Now,
Mm-hmm.
the reason it blocks one of them is you might have a case where switch 2 need to connect directly with switch 3 and it has nothing to do with switch 1.
Yeah. I
So
was thinking.
right, so they need a way for these two to communicate. So it's going to consider this port here designated and then call this one blocked. And that's why you see here switch 2 x0/1, it's a forwarding port, uh, and it's the designated port. So the designated port is the port on a LAN that is being used to forward traffic just for that LAN segment. So if you look, just for this LAN segment, nothing else, just for this LAN segment, the port that is being used to send traffic on that LAN segment. Okay? That's making sense?
Yeah, yeah.
Okay. All right. So now the timers. The hello timer is 2 seconds. So every 2 seconds, it's going to be sending out the BPDU, the Bridge Protocol Data Unit. Then it has a max age timer that is 10 seconds. Or sorry, 10 times the hello. So the hello is 2 seconds, so it's going to be 20 seconds. So the max age timer, 10 times the hello. This time is how long the switch wait before it considers the next switch dead. So let's go back up. So let's take switch 2 and switch 3. Every switch is going to be sending out their own LO, right? So if switch 2 does not hear from switch 3 for 10, it misses 10 hello, then it says, well, switch 3 no longer exists, it must be dead. So that's how it works. Similarly, if switch 2 don't hear from switch 1 within 10 10 hellos are missing. So it send one hello, and then 10 subsequent hellos are missing, which would be 20-second period. You don't hear anything from switch 1, then it says switch 1 is dead. Now, once that happens, the switches um, begin to they start over the election process. Anyhow they consider one switch dead, then all the switches will start over the election process.
Okay.
Yeah. All right. So the next thing is the forward delay timer. Right. Now, um, I'm going to come back to this, but I just want to stay right here. Initially, when a switch is booted, right, when you turn it on, it starts out with all the ports being blocked. So as you turn it on, every port is blocked. Then the ports are going to wait a while, and then they transition to a state called learning. Sorry, this transition to a state called listening. Then they stay in the listening mode for a while, and then they move from that to a next state called learning. And then in the learning state now, they're going to stay there for a while, and then they're going to make a decision as to whether or not they need to go back to blocking or they need to go to forwarding. So let's go again. They start out, all ports start out blocking. They will wait a little while, then they go to listening. They stay in the listening mode for a little while, then they go to learning. They stay in the learning mode for a while, and then they have to make a decision. Should they go back to blocking or should they move to forwarding? Right? Now, this 15 seconds with the forward delay is the delay is the time they stay in each of the states. Right? So as it says here, a port stays in an interim listening state and then an interim learning state for the number of seconds defined by the forward delay timer. So whatever this timer is the time it's going to stay in those states, the listening and the learning state. Right? Make
Yes.
sense?
Yeah, yeah.
Right. So that now is the combination of the max age timer and the time it stays in the listening and the time it stays in the learning works out to be 50 seconds. Now, why is that 50 seconds important? I'm going to just go back up and show you. To the slide with the one with the PCs, like this. So, let's work with switch 2. When switch 2 was initially booted, right? And we're going to use a port that connect to the computer, Archie. So on this port, switch 2 is going to be listening for to see if it hear any messages, right? Like the hello messages. Now it's going to wait for 10 times the hello timer, which is 20 seconds. So that right now it has the port there, right? In the blocking state and just listening to see if it's hearing the message. After 20 seconds and it don't hear any message, it says, okay, well, let's put this now to the listening state. So it switched the port to the listening state. And it's going to keep the port in the listening state for 15 seconds, continuing to listen for messages. Now it's not going to hear any message because there's no switch connect on this port, right? So after the 15 seconds, in the listening state and it don't hear any message, it says, okay, I'm going to switch now to my learning state, and it switch to the learning state and it wait for another 15 seconds and it still don't hear any message. It says, okay, this port here does not have a switch on it. So because I'm not hearing any messages, right? If a switch was on the port, then I should be hearing messages. So it says, okay, I'm going to move this port into the forwarding state. Because as long as it's connected to an end device, then it should be in the forwarding state. Make sense?
Yes.
So that's how those stages work. So when you um, plug a PC into a port, it usually takes about 50 seconds. Assuming spanning tree is running on the switch, it will usually take about 50 seconds before that port becomes active. And that's what we see in Packet Tracer. So if I start Packet Tracer and make a connection, you'll see. So I'm starting Packet Tracer.
Yeah, I can't get on Spanish packet trace, so I'm gonna have to delete and sign up again.
Okay. What? You don't remember the password you had used?
I remember it's save on it, but I can't remember it.
Okay. I never save passwords on thing, I will make sure I always have to type them in so that way I remember
Yeah.
them. The better thing to do is to try and reset the password. You hear what you do?
I did
Um,
that, but I don't know when I get the emails reset.
where you reset it from Packet Tracer?
Yeah.
No, don't
No, no,
reset
no.
it
I forgot the password option.
from Packet Tracer.
Yeah.
No, don't do it from there. Um, try to log into netacad.com and reset the password from there.
Oh,
Yeah.
just saying something about that, you know.
Yeah. So you don't have to sign up again, but what you
Mm.
do, well, I'm going to show you in a little while. So here's my packet tracer. So let's get a switch. Shouldn't matter which switch. And then get a computer. Now we need a straight through cable. And it's going to take 50 seconds for this port to become green. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Yeah, I think I might have started my count late. I was trying to make sure I get it by starting at 10, but I might have, very likely more than 10 seconds had passed by the time I start counting.
Okay.
Yeah, let's try another one.
So the switch was in it learning, listening and learning.
Yeah, so it starts out from blocking, then it goes to listening, then learning, and then forwarding.
Okay.
One, two, three, four, five, six, seven, eight, nine, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Yeah. Yeah, I don't think my counting is right. But it's 50 seconds it should take. Alright, so that's,
Yeah.
sorry, say again?
Now, so yeah, maybe you use the 1001 method.
Yes, yes, yes.
Yeah.
Alright. Alright, so what we're looking at now is what if a switch, what if a port failed? Right? So we know we were using this port going straight up and this port going across, but this section here is where we had the blocking. Right? So what if this port fail? Then what should happen? This port should just spanning tree should just automatically turn this port on. Right? So in that case, and when I say fail, it could be that somebody plug out the cable, right? And then spanning tree will just automatically switch this port on. Good.
Yes.
So now there's another port state called alternate port. Yeah? Now the alternate port is the port on a segment that is going to be used to reach the root if the root port fail. So look at this network. I'm looking at switch tree. Remember, this is the root port right here. Right? So if something fail right here, and therefore using the root port we can no longer get to the root switch, then we'd have to go this direction to get to the root switch. So this port is the alternate port. So the alternate port is the port that will be used to get to the root if the root port fails. Get that?
Yes.
Alright, so this is just showing now um, the root port has failed. Right, that's what this is showing right here. And then what's going to happen, it says immediate change to forwarding. So this alternate port knows that it should then immediately change to forwarding and becomes the root port. So the alternate port will simply switch to be the root port. Then what's going to happen up at switch 2, while switch 2's root port wouldn't change, but this port here for switch 2 now becomes switch 2's alternate port. Because if the root port right here fails, then switch 2 wants to now use this alternate port. You see?
Yeah. Yes.
Right. Now, a key thing we want to point out here is that the alternate port is a port that could either be in the forwarding state or it could be in the blocking state. Because right now, based on this alternate port is going to be in the forwarding state. Right? See, it's a designated port, and designated ports are in the forwarding state. But before, this alternate port is in the blocking state. Right? So, alternate port can be either in the forwarding state or in the blocking state. Right?
Yeah. Yeah.
Alright, so there is one more port that port categorization. Um, And that now is specific to rapid spanning tree. So all of what we saw before was specific, was worked in both spanning tree and rapid spanning tree. But the backup port only works in rapid spanning tree. Now the backup port is a port that will be used to forward data on a segment if the designated port for that segment fails. So in this case, this switch here, F0/1, is a designated port. So it is a port that is being used to forward data on this segment. Now, if it fails, then F0/2 will be used. So F0/2 is the backup port. So the backup port is the port that's going to be used to forward data if the designated port fails. And the alternate port is the port that's going to be used to forward data if the root port fails. All good?
Yeah.
All right, so rapid spanning tree have some other specific things. It has link types. So it's going to classify the links now in terms of types. So it has point to point. So a port that connects directly to another switch is called a point to point. So we have point to point port. A port that connects to a non-switch device like a PC or a printer is called a point to point edge port. So we have a point to point port and we have a point to point edge port. And then a port that connects to a hub is called a shared port. So those are the three link types that we have with rapid spanning tree. So we would not have these with the original spanning tree, just with rapid spanning tree. Now, very often on networks we set up multiple links, right? And these can be used either to increase the bandwidth or to create redundancy. So looking at the same three switch network, but in this case we have multiple links between the two switches. Oh my, when I finish this slide, we're going to break here. Remember, we were supposed to break at 2 o'clock. I just realized it's 2:25.
Okay, no problem.
Yeah. So we have two links here and two links here. So this is just showing us that we could actually have the same spanning tree situation even though we have multiple links. This is actually the last slide. So when we come back, so we'll come back at 3 o'clock and then we'll just pick up with the next slide. All right?
Yes, no problem.
All right, good, good. All right, so let's break here and we'll meet again at 3.
Okay.
All right, so I will stop the recording.